We're talking about vector spaces, and these two axioms have to hold. So one thing we want to do is test a given set is a valid vector space. Does it obey these two axioms? Other things we want to do are find dimension and basis for the vector space. So let me go through a couple of tricks for how to do that. You're given like real examples. One little trick I'll call the ABC method. I think other people call it that as well. Let's say here's your set. It's a three-dimensional vector, but it has to obey this little rule that the third element equals the sum of the first two elements. What I do is set up a generic element, a generic vector. Here we could say, we'll call the first guy A, second guy B, and the third guy's got to be called A plus B because it obeys this rule. So you write this generic element. And we'll write two of them because we want to test addition. And when you do that, these better be different letters than these. They have to be different when we try to add them. Otherwise, you're not really doing the test validly. So then let's see what happens. Well, the addition, what if I add this to that? I go through the arithmetic, what that means. I'll end up with this, and you can see that this obeys the rule. This third element is the sum of the first two elements. It obeys the addition axiom. Do the same thing with scalar multiplication. And again, the third element is the sum of the first two elements. It obeys that rule. So it's a vector space. What is its dimension? How many letters did I need to write a generic element? In this case, just two, A and B. That's your dimension. Remember this guy? Just took one vector. Its dimension was one. Now, how do we come up with a basis? We want it to be linearly independent, right? The easy way to do that is I call it the 1-0 trick. Here's your generic element. You go through letter by letter, setting 1 to 1 and the rest to 0 in sequence until you've done all the letters. So in this case, I'll set A to 1 and B to 0. So I'll get 1, 0, 1. The second one, I'll set A to 0 and B to 1. I get 0, 1, 1. That's a basis for this vector space. If I had just a generic three-dimensional vector, R3, I need three letters to do it. Mention it's 3. The 1, 0, 0, 1 trick gives me the standard basis. So that's two tricks for testing whether it's a vector space, finding the dimension, and coming up with a set of basis vectors. It finishes basic vectors and vector spaces and all the concepts that come along with that, like linear independence and basis, dimension, etc. And let me clarify one term. We use the word space. For smaller dimensions, we can often draw things. When we really get down to what a space is, it's a set of things that obey certain rules. You can't always just sort of visualize it. When we're doing pure vectors and it's only 2 or 3 dimensions, we can kind of draw things. But if you start losing your ability to draw things and imagine them, don't feel bad. I did when I first learned this. I didn't know the difference. What am I supposed to imagine the space you speak of? Anyway, next thing we'll get into matrices, bring these concepts into matrices. But first, we're going to have to talk about just basic matrix arithmetic. Because when we talk about generalized vector spaces, more axioms that have to come along with it. Like, what do you mean by addition? What do you mean by 0? What do you mean by scalar multiplication? etc. That will be sort of another module, module 2. We covered vectors as much as we're going to.